button. Okay, gave me the information that I am being recorded right now. So, as I was mentioning before, I am very excited to introduce you to what is artificial intelligence. So artificial intelligence is basically a series of algorithms that were developed in the late 60s and 70s, but were restricted by the amount of technology that we had access to. So we couldn't really do much with it. The theory was there though. Until very recently, computers became more and more powerful, and suddenly your processor in your computer could run, some very interesting simulations. And what it is just a rule, a series of rules from mathematics. It's a fancy function. That's pretty much what it is, or at least that's what was supposed to be. So really the boom of artificial intelligence came in 2016 or 17 when a group of engineers released from OpenAI a new algorithm in reinforcement learning that could learn how to play Go and then how to play Dota. Right, and basically these algorithms became so popular because they were able to defeat like the most important players in the world. Right, like gaming is for some people a career, a very demanding, very challenging career, but it's a career nonetheless. So they defeated these people, right? And that's when they realized, oh my God, the computers are really smart, and there was a lot of media controversy and whatnot, right? So the thing is that I want you to know why we are coding. That's kind of like the most important thing. And with AI, it comes a lot of responsibility, right? Just like Spider-Man movies. With great power, responsibility comes along. So coding is a tool. Nowadays, just by coding, you don't get guaranteed a job. If you wanted to work in Google, for example, it is extremely competitive, but there is another assets that you need to acquire. Right, there is another kind of a learning that has to come along with it, specifically in mathematics, other formal languages. But if you specialize in other areas like, I don't know, biology, chemistry, physics, engineer of any kind, coding is nowadays an integral part of your life, right? The potential, the capacity of creating programs that suit your needs for research is such an empowering tool, right? So artificial intelligence is definitely, was taken with a lot of excitement. And then we realized that there is a lot of controversy, a lot of potential dangers that come with the use of this new technology. And in particular, of course, human beings in the history of always have focused on the militarization purposes, and like just turn something into a weapon. So that is definitely the most dangerous item in the list, is making sure that whatever you trained really understands what instructions you're giving to it. Because sometimes the analysis of the data like goes beyond the understanding of the person that programmed that data. So your first challenge is, as an engineer or as a programmer, computer scientist, is to understand what are you making? What are the boundaries of what you're making? Because it goes beyond your comprehension. So you need to be very systematic in the way that you build your programs so that you don't leave loose ends. The second thing is complete and automated production that eventually and almost unavoidably is going to replace, most jobs in the market today. So you have overpopulation and other problems, related to human existence nowadays. There is 7 billion people nowadays. It's a lot of us. And then, if you leave many people without a job because you want to cut budget, if you're a company, right, you want to cut costs just by automating stuff, then you leave a lot of people without a salary, right? So that would become a pandemonium. It's a complex pattern. And finally, the one that you guys probably have heard before is termed the singularity. So the singularity refers to the point in time when we are going to be able to engineer something that realizes or is aware of its own existence, right? Basically, some form of metacognitive self-realization, intelligence. So that point of singularity could be game over for all humanity, because we would no longer be the smartest entities in the planet, right? But that being said, I mean, there is a lot of speculation. The question is not whether or not we will meet the singularity. The question is when. Okay, so that is why it's important to know what you're making. Sometimes people speculate that the singularity will arise by trying to solve a hard problem. And of course, there's going to be someone who has to write that code. Okay, so what do we code? What do you guys and I are coding? So being a programmer, as I mentioned before, is no longer just a career path, but it's a tool for your career if you want to succeed nowadays. They're not inconsequential. Things that you do matter. That's why you need to be systematic, and then you also need to be very precise on the spectrum at which your program is working. That's a responsibility. Okay, people don't talk about it. If you go to YouTube, nobody's doing this, right? It's just like, oh, just learn how to make a reinforcement learning algorithm. But you need to understand what it is that you are underestimating. So not only the code, but also the theory behind the code. And if you really want to become a coder these days, it's important you also start learning other formal languages like mathematics. You don't have to, of course, like you can make a even successful career in programming languages, but once you get or dive into mathematics and statistics, you become necessary, and you also, most importantly, you become essential to resolve some of those problems that our civilization is facing, needs to solve right now. And that's the last point. So problems like overpopulation, plastic pollution, climate change are just three of the many problems that new technology can help solve. So engineers are working on this, but they are not the only ones that come with the solution, because nowadays everything that you do in a career is so specialized that there has to be a lot of serendipity, aka collaboration, right, in between people, so that you can really create something that you wouldn't otherwise create on your own. So today, though, we are going to be talking about from the beginning, on the 50s and the 80s, by creating the simulation of life. Today, we're going to create our very first simulation of a living organism. And we're going to do it with Pygame. So we are going to use this library, Pygame, to demonstrate the simple rules that characterize the animation. So basically, these are the rules. So if you have a live cell with 2 or 3 live neighbors, then you survive and pass to the next generation, right? If you are dead, currently you are black, have a black color in the screen, and you have exactly 3 neighbors, then you survive. Not only survive, like you are born, you become alive. That is the second rule of Conway's game of life. And then the third one is that every other case is just death, right? Otherwise, you would have an extremely very massive growth of cells. We'll see how it looks like. Okay, but those are the 3 main rules that regulate the game of life. So how do we implement this in Pygame? How do we do this in Python? So here is what I call the winner's recipe. It's just catchy phrase. So the first thing that we need to do as computer scientists is to analyze the domain of our data. That means see what pieces in the real world we can abstract in order to put into very concrete data definitions. Okay, that's the most important thing, really. Even before we start coding, even before our first for loop, our first while loop, we need to create these examples, these data definitions with their examples. And we usually start, actually not usually, we always start with the atomic elements. Atomic means that they are not reducible to any other data types. Okay, if you remember, data types are 4 in the primitives. So we have, can someone tell me what are the primitive data types in Python? What are the primitives in Python? We have 4. Can you guys hear me okay? You say yes, if you can. Excellent. Okay, so Joshua is going to say something. Justin too. Excellent. So my question was, what are the primitives? We have 4 atomic, non-reducible data types. Okay, excellent. We have the first one. Came along. It's a string. Nice. Integers, floats, strings, and booleans. Very well done, both of you. Yes, that's exactly correct. Integers, floats, those are numerical. Booleans, yes or no. And finally, the string, which is text, right? And strictly speaking, strings are a form of list. So it's right in the threshold of becoming a compound data type. But it's a whole conversation that has to do with how computers work, but yes, those are the four main elements. Okay, so we're going to use those four elements to create our very first data definitions that we are gonna use to define a position in X and Y of a living organism, aka a cell. Okay, and from there we're gonna keep escalating. Besides that, we're gonna need to specify a color or a state. That's gonna be a Boolean. Let's call it a state, just because a state can be alive or dead. Okay, so you have a cell that is alive or is dead. And this is going to be reflected in different colors, like white for alive, black for dead. Okay, so the interesting thing about Pygame is that at some point we can replace these colors, simple colors, by sprites, by illustrations, so that it becomes more dynamic, right? It looks like a real thing. But for now, we're just going to say we're going to use very specific colors. Now, I'm going to keep explaining, but I want you to think about what elements are going to be constants and what elements are going to be variables in this design. Okay, so we have three so far: position in X, position in Y, the state of a cell. Okay, and this is going to be part of its own data definition. So these three are data definitions on their own. They're primitives, right? They're integers, and there is a Boolean. And then we're going to transform this in its own data definition, which is going to be called simply cell. That cell is going to be in a grid. It's going to be an individual in our grid. Okay, so at each step of our animation, we're going to need to, this is the cell, for example, that's what it represents. Okay, we're going to need to analyze what the neighbors are, and based on that, determine whether or not we change these alive or dead scenarios, these alive or dead states. And then finally, we are going to do this part of deciding based on the neighbors, updating the cell, updating the grid of that cell, using now the while statements, for loops, and etc. Right? But before that, all of this, notice, like 75% of the analysis that we're going to make has nothing to do with programming per se. It has to do with defining the code, defining the data. Okay, so here is the game. So focus on a grid of 3 by 3. There it is. So we have where you have two colors representing alive or dead. Alive is white, dead is black. Okay, where the center represents the cell of interest. Okay, we need to focus on something. We can just analyze everything at once. We need to take one cell at a time and then put it in perspective of the grid. So this cell right now is alive. So we're going to count every of the 8 different neighbors that this cell has. At each point, for each cell, we're going to have 8 different neighbors. It's going to be the one that is on top left, the one that is, is up left, up center, up right, and is at this level to the left, at this level to the right, and bottom left, bottom center, bottom right. Okay, so those are we're gonna need to describe what to do or how to count each of these different neighbors. But once we have it, then we can start applying the rules. Hey, if one of these neighbors is white, then has a white color in this state, I want you to count them. Like, for example, how many alive neighbors this cell has? Oh, it has 2. Right? So we're gonna give the information. Oh, you have 2 alive neighbors. And because of the rules of Conway's game of life, this cell right here is gonna be alive in the next generation. This second scenario, if you have a cell that is dead right here, you have 3 neighbors, exactly 3 neighbors. It can be 2 or 4, exactly 3. Then you're gonna be alive in the next generation. So that is how it works. So you need to notice how everything is in perspective of your neighbors. Okay, and then we're going to apply that to the whole grid. So we're not going to do the Kahoot right now. Just now, I want us to start working on this because it's going to take us some time. And at the end, we just reinforce what we learned by going to the Kahoot. So just as a reminder, well-structured data defines good programs. That's just the basic, the basis of our course, right? Is we need to know how to create the data properly, because then we intuitively receive information from the program itself when we need to change something. Okie dokie. So I'm gonna paste this. Please just click on it and then log into Replit. So I'm gonna see you there. We're gonna move into the live session of today's course. Okay, okay, excellent. I see Justin right there. Um, yeah, there we go. Okay, so if you guys want to say something, let's have fun. I'm just going to ask you to put it in a comment because otherwise the program may have, right? Today's we're going to be like complex program. So if everything is there that is not commented and it's supposed to be a comment, then we can spoil some things. We can break some stuff. Okay, so let's start by, we already have the analysis of our data. So let's start by working on our data definitions. So the first thing that I'm going to do is to create some constants. What do you guys think is going to be a constant in my game? What do you guys think is going to be constant in my game? You can type it in the chat. You can also, I don't know, type it in there if you want, just as long as you comment it. You know what? Let's use the chat. Let's use the chat, otherwise it's going to be too chaotic. The cells will always be there, either dead or alive. Excellent, absolutely. So for that, we need to think how many, so for a cell to be in a particular position, you need to know how many cells you have per row and how many cells you have per column, right? And for that, we're gonna need to define it relative to the screen size. The first thing that we need to think about is how big is going to be your screen. And that's the same for all animations and all video games. How big is the screen? Okay, so the first constant, and notice I am writing constants in capital letters because I want the reader to make sure that they know that this is not going to change once I define it in my program. So let's create a particular screen. So in your computers, you can choose whatever screen size you want. But for this particular example, because we're working on Replit, I need to be, we're more restricted. Okay, so through error, trial and error, I learned that 820 and 640 is a decent screen size. Okay, so the other thing that we need to identify is, well, how big you want the cells to be. We define them in terms of pixels. How big do you want your cells to be? I put a number that is a multiple of 2 in there. Yeah. Somebody just put a number in there. Okay, 50. Good. I see that you're thinking bidimensionally. That's great. So here is a trick. You gave me a tuple because one represents width and one represents height. But because this is a square, right? We know that the width and height are exactly the same. So in this case, we're going to leave it as 50. It just makes the code, easier to analyze, especially to unpack. Right? A tuple you would need to unpack to say, oh, give me the first value, then the second one. But if it is only one, then you don't need to worry too much about it. Okay. So we're going to start with these two, and then let's start with our first data definition. This one is going to be simply called x, and it's going to represent an integer. So I want you to think about it as the position of the top left corner of a cell in the game. That's what it is. So let's create some examples of a cell in the game. There you go. I don't know what else that. Okay, so let's look at some examples. X0, what is the most basic example? What would be the default position in our screen? What would be the basic position? Now look at it. We are receiving primitives. These represent primitives of type integers. So there has to be one integer number in there. Okay, X0, someone is giving me 120 because that's the width. Yes. That's exactly correct. Let's leave this one as xmax, okay? Because that is going to represent the width of the screen. But that is not the most basic example. Most basic example, let's call it xmin, or yeah, just like that. Yeah, just like, okay, like that. It would be 0, right? It would be 0. It would be the top left corner of our screen. And then we have to define something in the middle, like let's say x1. Now here is a fun thing. Here's a funny thing. Like we can just say any number, like 30, like 50, etc. Because every x position is going to be separated always by the same distance from their neighbors. What defines how far in the x-axis we're going to have to go between different cells? is in the constants. Which of those two, the screen or the cell size, or both? What do you think? We have two constants. One defines the size of the cell, and the other one defines the size of the screen. So for x, each x position has to be separated by the same distance every time. We can't just arbitrarily choose what value of x we want. Otherwise, the cells will overlap. It always has to be the same distance. Okay, there you go. Excellent. Yes. So notice that cell size, as you pointed out, is 50. Is already embedded in a constant. So let's make use of that constant. We're going to call cell size times 1. Okay, that is going to be equal to 50. And then, well, how about cell size times 2? Well, that's going to be equal to 100, right? So you can see how the next cell starts 50 units afterwards. Now, if you are really meticulous, you will notice as well that we can also represent the minimum value of x and the maximum value of x relative to this expression. Okay, so it's going to be cell size times 0. Oh, oops, it's equal to 0, right? Which means that that is going to be equal to the value that we had before, is 0. How about the maximum value? What do you think? How do you think we can express this? So we know that we're going to need cell size, right? And we're going to need to multiply by something. But what number should we pick? Should we pick 10, 20? How do we know that that is going to be the last square in the x-axis? That's really the question, right? So I'm going to give you a clue. You have to use the screen size. I'm going to start here. So I'm going to say cell size times something. But that something is not going to be something that we calculate, something that the computer calculates based on what we tell them. Okay. Oh, I see a 4. Okay. So here you're going to need to specify, you're going to need to use the screen value at 0. That's the width, right? Because we're talking about the x-axis, that's the width. So, okay, so let's assume that the width of, well, no, this is not assume, the width is 820 pixels. So what happens if I divide this number by the total number, by the cell size? You know, what would happen if I divide the screen by cell size? So basically, we would obtain the total number of times that, the total number of squares that I'm gonna have in my program, right? So that's exactly what I'm gonna do. I'm gonna divide the total number of pixels width and divide it by the total by the size of each cell, so that I obtain an integer value, hopefully, that is gonna tell me how many squares I can fit in the x position. So someone do me the honors, just place in there the last piece that we are missing. What should we divide for? Excellent. Excellent, excellent. There you go. We might enter a problem here. Let's see. Print xmax. Let's see what happens if we print this. What's the value? No idea why it's updating Pygame, but oh, there it is, 819. But that's a float, right? 819.999. That's a float. So what we need to do is to turn this into an integer, so that now it turns this into, the integer. It rounds it up. So now it is an integer. So that is going to be the final value. Okay, the final value that x can take. Let's work on the next data definition. That is going to be y. So someone, in a minute, just give me a second. It is the same, but someone start working on the data definitions. Please give me y0, and then I'll work in the interpretation, the data definition. Excellent. Sorry, that was me. There you go. Now notice that the only thing that we really changed was, the reference to the screen. Instead of 0, the width, we pick the second value, the index 1, right? That's the index, which is high. Right? So I saw someone making the second data definition. Yeah, feel free to do that. Is great. Okay, so now we have defined a position in X and a position in Y relative to our screen. That's great. So what do we need to do now? So after that, we need to work on what else our cell is going to need. And that is going to be a state, right? It's going to be a Boolean, as we defined it previously. It's going to be alive or it's going to be dead. So let's create that data definition. It's going to be called a state. And this is going to be simply st. It's going to be a Boolean. Well, maybe we can turn it into an integer as well. We can, in nature it's still binary, right? But we can work with it as integers as well. And the reason why I'm doing this is because at some point, someday, who knows, I might want to create a third state or a fourth state, right? In which the color is no longer only black and white, but also red or blue, etc., depending on how long my cell has been alive. So for that, in order to account for that in the future, I'm just going to leave it as binary. So the state alive dead of a cell in the game. That's what it represents. So there are two clear cases. Please someone give me st0 and someone give me st1. And actually, I'm going to change this. I'm going to say A and I'm going to say B for alive and dead. So someone give me a state for alive and a state for dead. Good intuition. Now, notice though, in our data definition, I'm telling you, this is an integer. So it's not a Boolean type, right? It's an integer. And actually, it's good that you pointed that out because restricted to binary. Now it makes sense, right? It's like a numerical Boolean, let's call it that. Great. So those are the two clear and actually only examples that we have available. Now we are ready. We have the 3 primitive data types. Now let's create the actual cell. So let's create a new data definition that is going to be called cell. And one is one second. So this one is going to be a dictionary. Okay, that is going to contain X with the data definition for X, a Y value for the data definition of Y, and finally a state. A state for the data definition of the state. Okay, and this is going to be a cell in the game. So let's start by creating our first definitions. Now, before I just start creating examples, I need to analyze the context, because it is true that I can just create random cells everywhere, but I would like to create them relative to their neighbors so that I can have a clear example of how the interaction of these neighbors is going to be. This is what I mean. In a grid, I'm going to have something that looks like this. This is going to be the position 0, 0, 0, 1, 0, 0, 0, 0, 0, 2. Okay. This is going to be 1, 0, 1, 1. And actually, this is the actual cell that I'm going to be talking about. And the third one is going to be 1, 2. And the third one is going to be 2, 0, then 2, 1, and then 2, 2. Now, notice this. We created this kind of a square right here as comments. What it means is that I'm going to create cells based on this nomenclature. So I'm going to say this one is 1, 1. Okay. So my cells are going to be named like this. Cell 0, 0 is this one on the top left, as you can see it. And this is going to be equal to what? Well, it's going to have an X, and actually you can just copy and paste it directly from the example on the data definition. Okay, so let's give it some values. So let's use the examples that we created before. So let's place this X position in this X into using one of our examples. This is what I mean. Instead of this capital X, I'm going to use one of the examples, which is going to be X min and Y min. Okay, so this is going to be a square whose top left corner is right on the top left corner of this of the screen. That is what it's going to represent. And the state, well, let's say it's alive. There it is. It is alive. So that is that cell. Now the next one is going to be 0, 1. It's still the same row. Okay, and this one is going to have to be 1 after x min, which is x. Someone's typing it. Excellent. There you go. Yes, x1, right? And same with y. Excellent. Someone working the next data definition, which is 0, 2. There you go. I'm going to leave it there for you. So that is the first row. I'm going to work on the next row. 1, 0, cell 1, 1, cell 1, 2. Excellent. So in the case of y, we're going to refer to the y examples. Right? So we need y there as well. There you go. So just for fun, let's make some of them as well, just so that we can visualize them more easily. So, okay, so I'm working in the second row, which is in terms of our cell or of the cell that we're going to be looking at each iteration later in the main programming scheme in the script is going to be the row, the actual row. Okay, so here, notice something interesting. So we move down one cell. Okay, we move down one cell, which means that the previous one were constant for the position in y. They were not constant for the position of x, right? We move from the left, center, right, but they are constant in y because they're all at the point 0, so that they're all aligned. So the next one is going to be y1 here for all of them. Okay, and the same is going to change for x. It's going to be x1 and it's going to be x2. So at this point, we're working with 2 dimensions. That is why it might become a little more complicated. But the whole point is that we are simply, every time that we move one row down, we update the value of y for those cells, right? We change the value of y for those cells. But as when we are moving between columns from left to right, we are modifying the x value. So there has to be one last one. Excellent. Someone's working on those already. I'm going to let you work on those. Okay. I'm going to let you guys work on that one. Excellent. Good job. So now we have all the different cases that define a neighborhood. Right? Let's call it a neighborhood that define a neighborhood. So now let's use these already compound data definitions to put them in rows and columns. And that is going to help us visualize, the matrix that we are going to make. So I'm going to define a new data definition that is called cells row. Okay, and if you guessed already, probably we're going to use pairs, well, not pairs, triads, right? 3 and 3. So we're going to find 3 rows. So let me see. So we're going to call it a cell row. No, it's kind of misleading. Let's cell row, CLR. Okay, and this is going to be equal to a list that is going to have cells in it. Right? How many cells? Well, what's the boundary? What's really the limit? Is it 3 neighbors? Nope. No, it's not. So the boundary of how many rows we can have is set up, is limited by how many we can fit on the screen. Okay, even though we define only a neighborhood, we are not restricted to that. We need to include all of the rows in the whole game. All of the cells in one row for the whole game. Okay, so that is why the maximum value that it can take is cell defined as the screen divided by the cell size, just as we saw in the definition for X. Okay, so now let's give an interpretation. A row of cells is the game. Let's start with our example. CLR, let me see how I define the 0. That's not a 0 equals cell, yep, cell 00, cell 01, and cell 02. That's it. Now, someone define the next one, CLR1. And someone define the next one, CLR. Excellent. Yes. Now, we have our cell rows, the ones for which we define each of the different cells in the previous example, in the data definition cell. But now here is an interesting question. How do we automatically generate cells for each of the different cells that are supposed to be included in one row? Like you certainly would agree with me that if I try to create one cell for each of the row for each of the cells that I can fit in a row, is going to be a long piece of code. So I'm not going to do that. Instead, I'm going to let the computer do that. I'm going to create an iteration. I'm going to iterate over a certain range that you can guess is defined by how many cells I can fit in a row, right? And I'm going to iterate over all of those, creating one cell on the go. A while loop, yes, yeah, almost a while loop. While loops are based on conditions. You can definitely do it with while loops. You can absolutely do it with while loops. What we're going to do today is going to be used for loops, though. And more specifically, we're going to use a special type of loop that is called least comprehension. So you have seen, for those of you that you like don't remember clearly, standard for loops are like this, right? So you have something that looks like this. Say something. This is called the expression. The print part is just the statement. Sorry. So here, if you move this and put it on the left, then you created a least comprehension, and then you put it in brackets like this. See, sometimes it's more complicated than that, but that's basically the basis, right? If I run this, look what happens. So it's exactly the same result. You see an iteration that goes from 0 to 9, and the only thing that I did was taking this from its current, from the standard way to write it like this, and then just put it in the left side. That's it, right? So that would be the statement that uses this I value, which is called the pointer. So the pointer is basically something that you count. A computer uses. It's like counting with your fingers. Oh, you're in position 1, position 2, position 3, etc. Right? So we're going to use this. We're going to use this nice technology because it's concise, it's condensed, to create the fourth and last row, which is going to include all of the different rows. So we're going to simply call this one CLR3, okay, just so that we don't complicate ourselves too much. So let's think first about what is going to be the range, the total number of items that we're going to need to generate, right? That is going to be the just the range. So it's going to be defined by an integer value of a relationship. That is going to be something that you have seen already, a screen at 0, divided by the organism size, right? Someone finish it there. There you go. So that is going to be the I can just finish it. There you go. In the organism size. So that is going to be the range. Of course, we need to put it in the range, right? We need to wrap it in a statement that includes the range. There you go. So this is equivalent of saying for something in this thing, range integer of the relationship of how many squares I can stack in a row. That's what it is. Okay, and if I do that, I'm going to comment this so that I make it a standard view. Then we can make it fancy later. So what should I do? Well, for each of those, I should probably create a dictionary, right? Based on the definition of cells, which is what I did before. So what I'm going to do is just going to be create a dictionary, right? You know, all the elements that the cell needs. Now, keep an eye on these underscores because I'm going to do something special there. But everything else is the same. And actually, we're going to define a default value for the state. Let's make everything dead for now. So let's say a state dead. Okay, and that would be my dictionary. It's going to create this dictionary for all of them. Now, what goes in the underscores? So right now, I'm not going to manually say x0, x1, x2. No, I want the computer to generate this for me. How do I do that? Well, I'm already iterating inside of my for loop, right? So just by convention, just for convention, I'm going to call this I. And then I'm going to say, oh, okay, well, the integer of the cell size, how did I type this? I think it was like this. No, is without the underscore. There you go. Cell size times value 5. Remember, when we start a for loop in a range, we start with I equal to 0. Okay, so 0 times cell size is going to be the value 0, which is the one at the top left corner. Okay, the very, very beginning. And then it updates. It's going to be 1, it's going to be 2, it's going to be 3, just like exactly as we defined it when we calculated our x values, right? So someone finished the value for y, and then we can proceed to make it in a least comprehension format. Yes, so now that's an interesting part. So should we use I or should we use 0? What do you think? So if this is one row and you update Y, you're basically jumping across rows, right? So you need to use 0. Good, Justin, I like your intuition. Yeah, but in this case it's 0, right? Because we're talking about the same row all the time. If we updated Y, we would basically be creating squares in a diagonal. Yeah. Okay, so that value is 0. So I'm going to update it. There we go. And that's it. We've done it. Now, notice that right now, if I iterate something, like nothing really happens. So just for the sake of it, let's wrap this in a print statement so that we can see what we're doing, right? What we're doing right now. So let's see what happens. I'm going to run this. Oops, it says invalid syntax. State I missed a colon. Okay, let's run it. There you go. Look at that. How nice. So we start with x at 0 and 50 and 100, 150, just like we talked about. But notice that the y value doesn't change. It stays constant, right? That's exactly what we want. Now, the last thing that we're going to do, I'm going to get rid of that print statement because I just showed it for purposes, teaching purposes. But now the last thing that we need to do is to embed this into a variable. So if we wanted to do that, I would need to say, oh, you know what? Let's create a new list, something like this. So list like this, this empty list. And then for every time that I create a new one, I say dot append and then etc. Right? That would make it. That would do it. But this is when least comprehension is useful. Because as I mentioned before, you can simply cut this back and paste it before, and now you have a least comprehension. And now you can assign everything that is created here directly into your variable, like that. That's it. Now let me print CLR3, and if everything worked well, we should see the same thing being printed out. Exactly, there it is. Look at that. So the format changed because there is no syntactic arrangement, like it's not in rows, but like I have everything in one element. You see, so that's why least comprehension is useful. Okay, so that's exactly what we did it for the cells row. Now we're gonna use this cells row to create a columns row. To create a columns row. In other words, we're gonna add, right now we have all the cells in a row. We need to create all the cells for many rows. Right? How many rows is going to be the next data definition. So we are going to use new data definition that is going to be called data def cell grid. Now it's no longer a row. Rows are unidimensional, one dimension. Grids are two-dimensional, so we are increasing one dimension. Okay, if you wanted to keep going and turn it into 3 dimensions, you're absolutely able to do it, right? But now that you have this format, it's easier to just extrapolate what you need, make it fit your needs. So here we are going to use something that looks like this. So first, let's create a CG that starts for cell grid. And this is going to take, it's going to consume, is the name, the formal name, I guess, cells row. Okay, it's basically going to be a list of cell rows, right? So it's going to be a list of lists. What's the boundary? Well, again, it's going to be limited by the by the cell, the screen, but this time at 1, which is the height, divided by the cell size. Okay, and again, just to keep in mind, this has to be an integer value. Otherwise, you know, like there is no index 1.5. It doesn't exist. Okay, so interpolate the whole grid of cells in the game. So let's work on the first data definitions that we created. The first example for the cells row data definition. So the first thing that we're going to do is to create a CG0 that is going to be equal to, well, CLR0, CLR1, and CLR2. That's it. Now, if I print CG0, look how it has a new dimensionality. Look, it tells you you can reveal this information because there are 2 square brackets at the beginning. At the very top left, there are 2 square brackets, which means that each of the elements inside the first square bracket are in a list. And the items inside of that list are list itself. Okay, so this is exactly what we want. And if it gets confusing, don't worry about it because it is. So just trust your data definitions. Okay, we have been building this with an algorithm. That's why we can make it so fast. Otherwise, it would take a long time just to say, oh, I don't know what I did wrong. Let me tune this, let me tune that, you know, and you get lost. Okay, so it's confusing right now, but don't worry, trust on your data definitions. Now let's think about the second example. But the second example is going to take, well, a process of automation, just like we did in CLR3 in the cells row before. But this time it's going to create a set of rows for in a range. You know, it's going to try to fit as many rows as possible from up to down. Okay, limited by the total the height of the screen. So let's make it. I myself, I'm getting a little confused. So I'm just going to copy and paste this right now so that we can digest it together. Again, I'm sorry, I made this program some time ago. So here you can see a very convoluted list comprehension. Look at that, look at the thing. So what is going, you should read first the thing that is outside. Okay, this thing is the one that we're going to replicate right now. For y, which is the height in range, and is this exact same thing that we wrote before. You see a screen at the position 1, which is the height divided by the cell size, for each of the columns that for each of the rows that I can fit. Now, for each of the columns that I define in CLR3, okay, the total number of squares that I can fit in a row. So this Y refers to the total number of rows that I can have. The next one for cell in CLR, for C, let me check. Okay, so this is going to be the total number of columns. of rows, sorry. And then we need to work on create a new type of row that we're going to attach. I shouldn't have to erase this definition. Okay, there it is. While I figure this out, do you guys have any questions? Do you guys need a break? Let me know in the chat. You guys good? You guys following along? No questions. Awesome. Good, good, good. Okay, so that was the first part on the outside, right? So we're defining how many rows we can fit. Now, the other part of this list comprehension is using a helper function. So, but let's focus on not on this part, but on this part. Cell for cell in CLR3. So CLR3, we know is one row, right? Is one row that takes all of the different squares that we can fit in one screen. That is why we're using this example. And then this list comprehension is basically iterating over each of the different cells that make that row. So what I'm going to do is to say for cell in CLR3. Okay, so what is going to happen is this. Let's suppose that I can fit 10 rows in my, because of the height of my screen. So 10 times, you're going to do the following. For each of the cells in the rows, you're going to create a new instance of this cell. Okay, so you're going to create it, then you're going to pack it, and then you're going to create a new list. So for cell in CLR3, well, we're going to create a new dictionary. So the cell is going to be equal to dictionary of cell. So the reason why I'm doing this looks weird, right? So we know that cell is already a dictionary. But here is something very important that is going to save you a lot of time, a lot of bucks. When you are making two variables equal to each other, even if I call this thing a different thing, this cell is the same as cell 2 in memory, in computer's memory, which means that if you modify cell 2, you're going to modify cell as well. That is why I wrap it inside of a dictionary of a dict statement, so that it creates a new copy in memory, so that now this cell 2 is different from the original cell. Okay, that is why I'm doing. Otherwise, you know, every time we update one cell, everything would be updated in the same state. So I don't want that to happen. Okay, there's probably fancier ways to do it, but you know, that's the way I found it. I found it useful to make it. Okay, so the cell, and this is the interesting part, the cell, the value in the Y position is gonna change, right? Before, we didn't have to worry about Y, it was a constant, but because now we are working on each of the different rows, we need to update Y. So cell of Y is gonna be equal to, let me see what it is. Well, it should be equal to the pointer, right? There we go. So, cell size times Y. Okay. So what is going to happen here is that, again, Y is a pointer. It starts at 0 and it gets updated. Right before it was I. This time I just decided to use a different one. It's Y because it represents the height. So it starts at 0. So multiplying cell size by 0 is equal to the very top left. The left side of the screen at the very top, and then it creates all of the different columns at that exact level. Then it finishes that iteration. This is what I mean by going through all of the columns. Finishes that iteration. Then updates the pointer. Now it's equal to 1. Now it moves down in Y, and now it starts creating, you know, all of the same columns, you know, in the value of cell size times 1. Okay, which is 50, etc. Therefore, we keep moving down. We keep moving down. All right. So now this is the fun part. So we need to transform this into a list comprehension because this one is gonna be, so these are two statements. What I mean by this is that we're giving two instructions, we're giving two steps. Okay, I don't want to do that because, well, I don't want to do that because I'm gonna need to define a new list. Actually, I would need to define two new lists if I wanted to keep this format. Okay, what I'm gonna do instead is to create a helper function. I'm gonna tag this thing off, take it out of there, and say, oh, please assign a value of y, and take the following arguments. You're gonna take both the cell, and you're gonna take a position that is gonna be equal to the cell size. It's the same that I had, exactly the same that I had, times y. Okay. Yeah. Good. Okay, so that is going to be my function. I wish that function existed. That's how it works. You wish for something and then you make it. Okay, so we're going to call it, we're going to assign it here. New data definition is going to be called assign y, and it's going to take something, and that is the sixth. What does it consume? Well, it takes a cell, an item. When my data definition is called cell, it's a dictionary. And then it also takes an position in y. What returns? What does it return? Well, it returns a list. If I remember, oh, it returns a cell. Okay, it consumes a cell, it returns a cell. So it's basically just updating the value of y. The reason why this exists is so that it updates the current position of a cell in terms of how high it is, you know, in the screen. So this requires a purpose, and the purpose is going to be to update the cell, the cell's y position. There you go. Now I'm ready to create my function. Assign y, and then I'm going to call cell, and yeah, I've been calling cells, and then just y. Okay, and what I have written before just goes in there. That's how it works. And at the end, we just return it. Return that cell. Okay. And we're ready for the list comprehension. Does anybody want to try it? Would anybody want to try making a list comprehension of two levels? I'm gonna give you a clue. So you take this one and put it before the for loop that is right outside of it. Okay, so you do it like this. So you copy this, or got it? There we go. Okay, and this is going to be one list comprehension. We take the columns away, but there it is. We have our function. And then, well, we are still inside another for loop, right? So we are just going to take all of this, and we're going to put it out, and then we are going to add the square brackets. So that is how we create a list comprehension, and we can easily just create this, put it inside of brain, don't fail me now, put it inside of a variable. Okay, so there we go. So this should work. Oh boy, CG2. Let's see what happens if we try to print this. Probably an error. Yeah, of course there is an error. What does it say? Assign for cell in. Oh, there is no y. Let me copy the one that I had made before. Let me see what I did wrong. Okay, so assign cell. So this is the same for cell and CLR3 for y in range. What did I do wrong? Looks the same. Oh no, it doesn't. If someone sees the error, please. Oh, two brackets. There it is. There was a second bracket. No, there was supposed to be a second bracket. Ah, boy. Let me check. Let's run it. Oh, good. Phew, it was the bracket. Okay, so this is how our data looks like. But now we have the benefit that we have created all of the grid for the entire game. So now we don't need to worry about what square is what, right? It looks horrible because we're looking at it in text, but you know, it's everything is there. So let's corroborate, and we're gonna do that by unpacking a little bit the information that we just created. So let's call this CG1, right? It was the value. There you go. So I want to print all the elements in the first row, and for that I'm going to say the 0. Print everything in the first row. Let's see what happens. There it is. So we are getting y should be a constant, right? For each row. So x changes, there it is, x equals 0, then 50, 100, 150, great. How about y? Y is equal to 0 in all of them. That's perfect. If we say, hey, pass me the next row, CG1 at the position 1, we should get a value of y that is equal to 100. We are not. Look at that. We're getting CGI, we are getting a value of y of 2500. What? Why is that? I mean, it's still a constant, that's good. But we are getting a value that is too high. It should be 50, right? So let's look at what happened to our data. Oh, I see what happened. Okay, so notice in line 75, we're passing an argument that represents an integer value of the current value in pixels of y after multiplying it with, you know, cell size. So I pass that as y, but it's already digested, let's say. The calculation is done. And still, I do it again in line 72. You see, I'm doing it again. I'm replicating the process. But this time is not, I shouldn't use cell size times y. I should only use y. If someone wants to fix it, you can just fix it. Go for it. Okay, so we might start getting tired. So this time it should run. There it is, perfect. Look, y equals 50, and if I go to the next one, equal CG1 at the second position, look, y equals 100, etc. So now we know for sure that we have the whole grid. We just create a full grid with dictionaries that represent cells that are alive or are dead. Okay, so let's take a very short break because maybe even if you don't have questions, your brains might be fried. I know mine is. So let's play our Kahoot game, okay? And then we can, you know, advance a little bit more on our data definitions. Does anybody have any questions, though, or any comments, or something that you would like me to go back to? Just let me know, and I can go back. Okay, I'm going to give you 1 minute so that I can also drink this water. No, Justin, Joshua, any questions? Okay, awesome, awesome, awesome. Excellent. So let's play a Kahoot. It's going to be entertaining for a recap. So what I'm going to do is just to share the link that you can click on, and then we can just enter the game. Okay, there we go. I pasted it in the group chat. You just need to click on it, and well, you know the rest. Can somebody please tell me? Can you hear the Kahoot music? Please say yes or no. Can you hear the music? No. Oh, okay. I'm gonna stop sharing for a minute. There you go. Now I am recording. Okay. Okay, there we go. Thank you. Thank you, Justin. So here we are. So we're going to import the first module is going to be Pygame. Okay, because I mean that's all the infrastructure that allows us to render stuff and make videos. The second one is going to be rand. And what random am I going to use? I'm just going to import all of it. So I'm going to create a condition. Sorry, I'm going to create a constant. That constant is going to be the probability that a cell is alive. You're going to see how important this variable, this constant is. So it's going to say chance alive, and I am in line 12. What probability would you guys want? Someone please just put it in there. In line number 12, a value that goes from 1 to 10. From 1 to 10, just, put a value there in line 12. Yeah, give a value to the constant chance alive, can go from 1 to 10. It is better we do it for 100. Anyway, so I'm going to create one now. The thing here is the scale is up to you. You could say a value that goes from 0 to 1, right? But in my case, I don't want to deal with decimals. Some people like it, I don't. So I'm just going to say, I'm going to define it from 1 to 100. Could be 1 to 10 as well. I'm just going to say, I don't know, 20 represents 20%. Percentage. There you go. So that's our constant. So that's what we're going to use. So let's go down to line 84. So for each cell in the row, if random dot rand int, random integer from 0 to 100 is less or equal than the chance of being alive, then I am gonna change the state, and I'm gonna make it equal to, what was it? ST. If someone can do me the honors in line 85, just make that cell alive. There you go. Excellent. We're ready. We're ready. But now we just need to put this into a variable, right? So right now I'm just gonna. I guess it's getting a little not complicated, but it's getting a little saturated with all of these comprehensions. So I'm going to leave one with the standard nomenclature for nested for loops. So I'm going to say CG2. Remember, we are still in the data definition for cell grids, right? I'm going to say you're going to be an empty list, okay? And I'm going to have to define a new, what am I doing here? Yeah, it's just I'm gonna need to define 2 empty lists. That's not something I want to do. Okay, sorry guys, I'm gonna need to use this comprehension as well. So, but luckily, I mean, we can turn this into a helper function just like we did before. Make alive. Okay, if someone would like to create a function down here, I will be super grateful. So I'm gonna leave this information here commented. I'm gonna call it make alive. He's gonna receive, should receive. Yeah, so work on that data, on that function, you feel like it. And then I'm gonna be working on the definition. So this function is gonna take 2 arguments. The first one is gonna be the cell itself, and in second, the chance of being alive. Okay, so those are going to be the 2 things that this is going to consume. So we're going to make this signature. First, we're going to take a set of the data definition cell and the constant chance of being alive. And what it returns is going to be a set. Okay, it's going to return a cell as well, just like we did before. So the purpose of this function is to update the cell's state to make it alive if chance, if chance permits, let's call it chance permits. Okay, so there we go. So now we're ready to work on our data definition. So I see someone trying to write something in line 86. So I'm going to help you for that. Information that you need is already in line 87 and 88. Okay, so feel free to write it yourself or just uncomment it. Excellent. And down here, we just need to add the arguments to line 93. It's going to be the cell and the chance of being alive. Good. Okay, so I would say like the class is over. Technically, it's 6:30, but before we leave, I just want to show you the I'm going to show you the rendering next time. Okay. I hope today wasn't, like a little frustrating because there isn't a lot of things going on. But next week is just gonna be graphics, and it's gonna be pretty cool. Alrighty, so I'm gonna stop sharing this. You guys have the link if you want to go back to it. Feel free to fork it, and then if you